Okay, for once we point the camera in the other direction. I need to know who you are, so I take pictures. Smile. Ah. Yeah, well, I mean, sorry, but there is also a bottle of some strange fluid in front of you. I don't know, I guess I should have charged batteries. I will then print these out, and then you can put your name on it. You can also veto, but then you have to give me another picture. I have no other way of remembering your names. Ah. Few more. Well, anyways, I get always these comments doesn't refer to students as individuals, and I guess it's true. So maybe I need to make an effort, right? Okay, so okay, well, welcome to 240. Okay, so who went to ISSCC? Not quite everybody, but about half. Huh? Okay, we were talking about current sources. I wanted to ask you first something. If you want to make a low noise current source, one that puts out a lot of current and little noise, what are you going to do? What is the key ingredient? Yeah, and you should use the microphone. Yeah, the large overdrive. The carrot, if you want low noise, the only thing you can do is voltage. You got to give your transistor a lot of voltage across it, make a huge V star, right? Or VDZ, or whatever you like to call it. There is nothing using another technology doesn't help. Using somehow bigger transistors, so it will lower the flicker noise perhaps, but it will not lower the thermal noise. So you need voltage headroom. If you want to generate a high output impedance, what are you going to do then? For high output impedance. Oh, yeah.
You make cascode?
Yeah, exactly, right? I mean, to some extent, you can try to use a long transistor, and you may be able to double the output impedance or so. If you use a cascode, by what factor can you increase the output impedance of a transistor? Yeah, basically by GMRO, and GMRO is between 10 and 100, right? So if you want to get a lot higher gain or a lot higher output impedance, right, use a cascode. If it's just a little, maybe you can use a long transistor. Okay, so cascoding. So here is the circuit that I'm using to investigate this. Now, if you use a little more zoom, please. Thank you. Well, not too much. Okay, so again, and I've mentioned that several times, when I investigate a problem like that, I use an uncascoded transistor, and I also use a cascoded transistor. And I set up the VGS here with a current mirror and bias this one sort of easily and sloppy just with the voltage source. Later, of course, we're going to have to talk about it. In general, that reminds me, in general, when we sort of do these experiments with SPICE, we do sometimes things that we're not going to do on the IC. I got one question regarding the homework and that huge resistor that I suggested you would use to bias the thing. Well, in reality, we're never going to build that huge resistor. When we actually build the circuit, most often the way we are going to bias that kind of capacitive feedback thing is using switches. I think we briefly talked about that. And so but for just analysis simulation to get quick idea, so we can use these ideal elements that in SPICE. It's no problem, right, to implement it. Okay, so I just did a quick check, right? Of course, this is actually the output resistance without cascode, and then the cascode sort of improves the output resistance. And of course, there's sort of a question. Well, in this scheme here, for the circuit that I've used, we not only increase the output impedance, but if you really want to get reasonably high or out, and here actually up here is 100 mega ohm, so that would be pretty decent, right? But then we need quite a lot of voltage across certain transistors. So in other words, the Vmin here is now 900 and some millivolts, and that's kind of the big game. One of the concerns in building a cascaded current sources is how are we going to minimize the amount of voltage needed across the stack of transistors? And the big thing to do here is to replace this voltage source that has been generally set here to 1.5 volt to something that gives just enough voltage to M1 to get a reasonably high output voltage, but not anymore, because otherwise we are eating into the Vmin, into the minimum voltage that we need across the entire stack of our cascode. So now we have to look at circuits that do that. But before really we do that, let's look at the trade-off, just sort of how much voltage, how much VDS should we have across M1, right? So in the good old days of the lambda and square law model, the answer was very easy. We needed VD set across M1, and then it was in a high output. It was in saturation. We got the best possible, incredibly high output resistance. Now we know that that's not true, right? And so we have to make some kind of a trade-off there. And to investigate that, I chose carefully the bias on my cascode such that the VDS1 was equal to a factor K times V star of M1. I didn't use VD set of M1. I prefer V star, right? Okay. And so then I ran this simulation here, and I mean, what does it say? Well, here is sort of for reference no cascode. Now, this is a logarithmic plot, so even though these curves sort of are relatively close together, they're actually almost an order of magnitude apart in output impedance. So actually the output impedance improves substantially as we add the cascode. So the green line here, we add the cascode and we set that K, this K factor, to just 0.5. Okay, so according to the, I mean that's something that you probably wouldn't do based on the old lambda sort of thinking of thing where this K ought to be 1, right? And V star is equal to VD set. Right? And the interesting thing is here we still get a pretty good boost in output impedance. Then I increased K. I made K1 and K. The blue line finally is K1.5. And I could yet further increase the output impedance. So why did I run this simulation? Well, we want to figure out what is a reasonable value for K. So based on, here we have the simulation data now, what is a reasonable value for K and why? Do you think? Well, let's sort of go at one extreme. Suppose that we want to get really very, very high output impedance, that was our one most important design parameter. How would we choose K? I mean, now it's trivial. You ought to know that.
Could we look at the output resistance plot from the two previous slides and then find the optimum over there? Peak for the single transistor case. We bias our K.
Oh, okay. Maybe we could go here. Well, I want to keep it simple, right? I mean, the best one in terms of output impedance is the one with highest K, right? The blue one, right? It's really as trivial as that, right? Okay, so if we want really high output impedance, well, we choose K large, right? That's easy. But now, if we don't want quite as high output impedance, should we scale back K? Well, if you look at the slide, it tells you. I would argue no. And why not? Yeah.
You might rather just lower the output voltage headroom that you need.
Right, exactly. It seems to be there is no penalty of making K a little bit too large, right? If we choose a high K, and then we have a low Vmin, well, we haven't won anything, but we haven't lost anything either, right? If this is our Vmin, then K basically doesn't matter. Actually, it doesn't help us to have a cascode either, but sort of no big deal, right? If, however, we wanted to have higher impedance, or for some reason our Vmin is larger, so then the higher K helps, right? If in fact we are operating somewhere up here, well, then the blue line gives us a benefit over the smaller K here and here, right? So I think these. So what the conclusion from this is it's better to err on the large side for K, right? And so that's very good to know. Apparently, I don't need to fiddle and optimize and know a whole lot and so on. I probably would rerun this simulation if I had a new technology, just to be sure that there isn't some. Right? We haven't exactly looked at the physics of why this is. Right? So to be a little bit careful. But at least here for this process, for these transistors, very solidly, this says that don't try to save. I mean, improve your optimize your voltage headroom, your Vmin, by picking just the right value for this K. Make this K generously large, larger than 1, and even then, if Vmin is sort of on the short side, right, on the small side, we haven't really lost anything. Okay, so that's a very good thing to know, right? Because it can save us a lot of wasted time trying to push buttons on SPICE to optimize something that can't be optimized. Right? After all, we want to design interesting circuits and not play with the simulator. Okay, so actually, I even changed this. This is actually not quite the right conclusion. We need new of these pens there. Not really working. So this is not quite the right analysis. It's really K larger than 1 is apparently the right choice just about always. Okay, and there is no penalty. Even if our route isn't that big, there isn't really a penalty if we chose K somewhat on the large side. Okay, now we sort of know what we want. That puts us into a very good position for our next thing. And our next thing is to figure out how we set now the voltage on the gate of that cascode device. And for that, we need some kind of a circuit, right, that does that. And ideally, that circuit would be something where we really just could program in a K or so, right? We could program in K 1.2 or 1.3 or so, and then it would just do that. And it would do that over different processes and variations of, let's say, mu and Cox and VTH, and maybe even if we go to a different fab or so, then it still would just do the right thing, right? We really don't want that it depends on these parameters or circuit, because we would have to redesign it all the time, right? And so the question is, how can we do that? Well, I show you now a whole bunch of solutions how to do that. And normally I don't like that. I don't like to give you a catalog of solutions. Why not? Well, because I ought to teach you the one best thing, right, and be done with it. Why all the other stuff? Turns out that there is no one best thing. And so I actually present 4 solutions that all have something to go for them, and they also have all something to go against them. So really, which one you use, when, and so on, it's sort of pick your evils and your benefits, right? So, but they're not very complicated either. One sort of issue is with designing these is that for designing these, we really rely on the square law model. Why? Well, because our V-star model really doesn't say anything about large signal, and here it's VGSs and so on that we are setting, right? So we need a large signal model, and we have nothing better than the square law model. So that's what we do. So here is the first solution that we want to look at. So here is the current mirror, and here is the cascode device. Oh, these are really. You should put in to get new of these pens. They're not working anymore. So I'll do it in black. So this is the cascode device that gives us the high output impedance. This is the current mirror that that's the current, right? This transistor here, forget for a moment about this M5, but this transistor here, it computes the right VGS that is needed here in order to have the correct VDS across M1, right? Well, now if we run the same current here and the same current here, then the voltage. Let's assume for a moment we were completely in the square law model. Then what we would want, and k equals 1. Then we would like the voltage that we want here is 1 VD1 set, right? And here we would have VGS2, and this VGS2 would be equal to VTH2 plus VD2 set. And this VD2 set, if both transistors are the same size, would be just equal to VD1 set, right? So the voltage, the VGS4 that we have here, we really would, that's going to be VTH4 plus VD4 sat, right? So in order, because the voltage between here and here is equal to VTH2 plus VD2 sat plus VD1 sat. If all the VD sats were equal, then we would like this VD sat just to be twice as large as the VD sat of, for example, M1, right? So now if we use our square law equation, then we have ID equals 1/2 mu Cox W on L VGS minus VTH squared. Actually, I could have said VD sat here, right? So the current's the same. Said that, but we want to double this thing. Well, then we need to reduce this by a factor 4, right? Because of the square here. Okay. So it's as simple as that. Of course, it depends on the square law model, but we have so many assumptions and this k-Fudge factor and so on. Unfortunately, we found out that this is not very critical, right? So that's what we're going to do. We are just going to make the W over L of this transistor 1/4 of the W over L of the other transistors. Now, just like we did when we made ratioed current mirrors and so on, we don't actually do that by really making the width or the length or so of this device different, but we're going to use multiple devices to get a reasonably accurate ratio. Now, this device is 1/4 of the size, and here is again one of these things that you can do in SPICE, and you don't do in reality. I just set the M of this device to 1/4, right? In the actual layout, you would set the M of this device to 1 and the M of all the other devices to 4. But that's more typing, and I'm lazy, and so I do this, okay? All right, so then again a bunch of simulation results. So I actually call this thing M, right? This factor M. Here on the slide it says K, but it's really M, the factor by which I reduce the size of M4 compared to M1 and M2. Okay? And the 1/4, that's what you read in, let's say, Gray and Meyer, so a book that teaches the lambda model and all square law. So then we get this, and obviously, I mean, if we make it smaller, then it doesn't work as well, and if we make it bigger, it works somewhat better. Right? So here also, just for completeness, right? It's so nice once you have it in Spice, you can play a little bit around it and see what you can learn out. In addition, I ran it through the nominal and the slow and fast parameters and found that there is actually not that much of a difference. The output impedance goes up a little bit for the slow case, but at low voltages, low VDS, really we didn't get low Vmin. We really get no much difference. Okay, now before I forget, there is one more thing that I need to talk about, and nobody asked about, and that is this transistor M5 here. What's the purpose of M5? Well, this whole circuit here really has several functions, but two of them are, one of them to get high output impedance, and for that we have this cascode device. But the other thing that we shouldn't forget is also we have a reference current here that we presumably set up with a fancy band gap or something like that, right? And it's maybe fairly accurate. The other thing we really expect is that the current that's running here is within very small variation, within very small fraction, equal to this current here. Well, in order to make this equal, we have to have this current mirror here to have an exact ratio of 1:1, for example. Right? Now we've already looked at we don't put in resistance in the source or stuff like that, right? We make these devices, of course, exactly the same size. But there is one more thing that we have to keep the same in order for the current here and the current there to be the same. And what's that? VDS, right? VGS is already the same for both devices, but the VDS also needs to be the same. So in other words, the voltage here and the voltage there must be just equal and the same. Now, normally in a normal current mirror, M3 is simply diode connected, and consequently the VDS is whatever comes out of this diode connection, whereas essentially VDSAT plus VTH, right? And and this device here has approximately VDSAT across it times maybe 1.5, right, or so. So the voltage, the VDSs of these two devices are different. Well, M5 does nothing but make sure that the voltage here is actually just equal to the voltage there. Okay? So it's sort of, if you leave it away, nothing worse is going to happen except that you're probably going to get a few percent mismatch in the current between here and here. But other than that, the circuit will still be functional. But because transistors are small and so on, and a little bit more precision rarely can hurt, right? Most of the time, of course, we're going to put this transistor in. There is, of course, the catch that if we had a very small threshold voltage, let's say this was a native device with threshold voltage 0 or so, then this connection wouldn't work, right? Because it would put this device terribly into trial region, and then it actually wouldn't work with M5. But usually because threshold voltages are sort of large, 500 millivolts or so, and VDSAT, so V-stores are small, 150 millivolts or so. That's not a problem. But you got to look at it, right? Just keep that in mind. One last thing, one more thing that I want to say is that this circuit is sensitive to the body effect. Why? Well, because when we set these two equations equal, we not only relied on all the VDSATs being equal, but we also relied on the threshold voltages being equal, in particular the threshold voltage of these two transistors. But because this guy, M2, has its source at a higher voltage than M4, its threshold voltage will be a little bit larger, and consequently the voltage, VDS, across M1 is actually somewhat smaller than what we would expect. So that's inherently sort of a disadvantage of this circuit, but we can again, it's not that a bigger problem because we can just choose this M4 a little bit smaller than a quarter, typically 1/5 or maybe even 1/6, right? And that doesn't seem penalty. The other constraint for this circuit is that we really depend on the length of the cascode device and the length of the current source being equal, and that's not always optimal. Actually, very often in a high performance amplifier, we're not going to do that, and so in that case, the whole thing kind of breaks down. You can't use this biasing circuit. Although another thing that goes for it is very simple, right? Okay. So here is just a small variation on that same circuit. Here everything's the same, but that transistor that before was a quarter or a fifth the size, M4, has been replaced by a stack of usually 5 or 6 devices that are all of the same size, all diode connected, but they sort of make up. Here, in a way, you're actually going to increase the length of the transistor rather than decreasing the width of the transistor. The advantage of this circuit is that because the sources of all these devices, they sort of slowly lift up, this sensitivity to body effect is a little bit reduced here compared to the previous solution. Okay, fine. Now, this circuit is a little bit fancier, and ultimately, not in this version, but ultimately we will find a way on extending it so that we can use different channel lengths in the cascode and in the mirror transistor. Okay, so how does it work? Well, so sort of similar again. It has this device here, a diode connected again, but instead of tying its source directly to ground, it is stuck in series. It's just one single additional transistor that is purposely sized smaller so that it will be in linear region. Okay, and the exact analysis on how to size these and so on, this is again based on the square law model. It's a little bit involved. There are lots of equations. So I don't want to go over that. I put all this here so you can do that by yourselves. It's basically straightforward, right? And the point is, when we set up these equations correctly and solve them, then we can make the VDS of this transistor M5, we can make that a multiple, or I call it here a factor, or times larger than the VD of M1. Right? So we really set up this this relationship of VDS5 is equal to R times VD1 SAT. And this R would, of course, then be basically the value that what we called K before. Right? So typical R's are like 1.2, 1.5. And of course, because these devices, they're all equal size and they all run the same current, the cascodes that pin the voltages, all these voltages here at the same value. Consequently, the voltage, this VDS5, is simply copied over here. VDS1 is equal to VDS5, right? Which is really what we want at this point of the equation. Okay, so that's That's a useful circuit to use. And so as I mentioned already, the nice thing now is that we can actually we can make it that that we can operate with different channel lengths. And I've cooked up an example here where I do that. Here I haven't varied the channel lengths at all. So this is the old circuit that we had on the previous slide. That is simply this structure here that I put here, copied here, and it's set up the same way. So this really sets up the VDS5 that later we want to use to set up the VDS1. A little bit less zoom. Okay. Yeah, thanks. So now here the cascode device here is now shorter channel length. Like frequently we will want to do that in our amplifiers. Okay. And really the carrot why we do that is that then our Vmin is a little bit smaller. Okay. So because of that we cannot tie this voltage, we cannot tie this gate directly to this gate over there, because the smaller transistor actually needs now a smaller VGS than this transistor over here. But we are not really, it's not really the VGS we are interested in of this device. What we are really interested in is this VDS5, right? All we want to do is we want to copy this VDS5 over here so that this VDS1 is equal to VDS5. So how do we do that? Well, we simply set up a mirror that instead of tying this one here to ground, we tie it to this level here that we sort of treat like a voltage source, like a fixed voltage, right there, VDS5 that we are interested in, and then we rely on this cascode sort of arrangement to simply copy the voltage at this source over to the voltage at that source, again because the transistors are the same size and the currents are the same, so nothing else can happen. Now, of course, we got to be a little bit careful. If here we have I0 and here we have also I0, then the current that's flowing here in this device is going to be 2 I0. Okay? Consequently, compared to the previous slide or the previous circuit where we didn't have that, we have to double the width of this transistor here. No big deal. I suggest that it's not a homework or so, and it's up to you whether you. But I suggest that you set up this circuit as a SPICE sub-circuit, right? Parameterized where you can dial in different lengths and different bias currents. And that will later prove very convenient for homeworks, because very often you will need a cascode, of course, in an amplifier that you're designing, and you need to figure out what is the right voltage there. You can, of course, try to figure out what, 1.175 volts or so. You can try to figure that out and stick it in and so on. I found that to be extremely inconvenient. First of all, how do you really figure out that voltage? You have to run a bunch of simulations, right, to figure out the constant VGS to put on the gate of your cascode. Secondly, if then you use fast or slope parameters, or if you change the temperature in your simulation, it's going to be all wrong, right? So when I use cascodes, I pretty much always use a circuit like this one. I do not bother with setting up constant voltages. Okay? And but the trouble, of course, with this is that it takes quite a while to hack this thing into SPICE. So that's why I have this sub-circuit that I just keep reusing and type in just different specification. All right. This now is almost only for completeness. There is yet another high swing biasing circuit. This one is insensitive to body effect, unlike all the other ones, and you can look at it. It does have a disadvantage, and that is that we need fairly extreme, a little bit more zoom, fairly extreme transistor ratios of 1. Most transistors ratio 1 to 1, and then this one is 1/16. And 1/16 you often get very small, or in other words, the 1-on-1 transistor is then really big. And of course, yeah, so sort of clumsy makes a huge biasing network. In general, you will find that biasing networks, they're a big deal. They take quite a bit of area. They can get similar in size as the amplifier that they're biasing. And also, they often dissipate a lot of power, which is very unfortunate because in a way, right, this is power that we really ought not to have to dissipate. But in practice, we need it, and so very often half of the or a third of the power of an overall amplifier is actually in the biasing network. One of the key reasons why we need a lot of power is that, of course, we could have in our amplifier, we could have a large current, a milliamp or so, and then in the bias network only a couple of microamps, right, ratioing the current mirror. The trouble of doing that is that the impedance basically is 1 over current, so that makes the output impedance of our biasing network, all these biasing voltages, very, very high. And so ultimately, right, this is probably the output of an amplifier. That output of that the output of that amplifier is going to swing up and down wildly, right, as a function of our signal. Well, because of capacitive coupling, then this node, the bias for our cascode, is also going to vary, and that of course is a that then can be a problem. First sort of the bias network starts sort of acting on its own and may actually the amplifier may settle slowly because it has to wait for the biasing network to settle for all strange things. And the other thing is very often these biases are shared among different amplifiers. Well, then we couple the signal from one amplifier right into another amplifier. So very often, actually, I play it safe, and I do not share these biasing networks between different amplifiers, just for this reason that feeds so it's a dangerous thing. Okay, so by of course keeping this at low impedance, then we have here large capacitance and also sort of a reasonably low GM that pins this voltage better. We get less variation there. Okay, so that was cascoding. So if we want to, again, getting back to, if we want high output impedance, what are you going to do? If it's just a little bit, then we might just increase the length of the transistor by a tad bit. If we need more, then we use a cascode. What do we do if we need even more? Yeah, you know that, right? Puts you asleep, so. No, maybe you. So, what are we going to do if we need yet higher? I mean, you're going to run into this problem. You're going to have a hard time on the project if you can't answer this question. What are you going to do? You need yet higher output. You want higher gain in your amplifier. You're not going to meet the spec. How are you going to get more gain out of this thing? Yeah, exactly. Stack up yet another cascode. Use 2. If one cascode's good, well, 2 are better, and 3 are yet better. The trouble, of course, is that in a 1-volt supply, you pretty quickly sort of forget about that idea. So one way to get around that problem, one way to get more output impedance without adding another cascode is to use feedback. And generally, the scheme is sails under the name of gain boosting. Now, in your whatever undergraduate course where you probably studied feedback, you've seen that when we apply feedback to a circuit, not only do we sort of stabilize the gain, but we also change the terminal impedances, right? Depending on the type of feedback we are using, the impedance can go down, right? For example, in an operational amplifier, we want to have low output impedance driver speaker or so. So we want to have a fraction of an ohm output impedance. Well, we can use feedback that lowers actually the output impedance of the open loop amplifier by what factor? 1 plus T, right? And what is T? It's the loop gain, right? So we can lower the output impedance by the loop gain, 1 plus T, the gain of our feedback loop. Well, we can also, in other configurations, we can boost the output impedance by a factor of 1 plus T. Right? And that's what we're going to do in gain boosting. Okay, so here is the circuit that does this. Now it contains a whole bunch of stuff. This is the current source transistor. This is the gain boost cascode, and then this is this feedback business that further increases the output impedance. Right? Okay. And then here, just for comparison again, I have just the cascode, but no feedback loop, no gain boost amplifier. And here I have just the transistor without cascode. Here I have some kind of a biasing circuit. Now here I didn't use one of these high gain, high swing bias networks. Here I simply use two diode connected transistors. Again, this is entirely to sort of make a simple example or a simple test bed where we can figure out what's happening with such a gain boost amplifier. We already know how to produce the right bias voltage for our cascode, and there are better circuits than this one, right? But here I'm over that now. I'm using a simple circuit here because I don't want to complicate things. We understood the other part. We understood already. Okay, so how does this work? Well, one way we already talked about. Really, what we do is we apply feedback here, and that somehow miraculously and out of some equations that you derived in some undergraduate class increases the output impedance here by a factor of 1 plus T. Now, what is actually the loop gain? Well, here there's an amplifier, there's a gain of 10. This thing here for this amplifier looks like what? Yeah, like gain of 1 or a source follower actually, right? And so the loop gain is about 10. So you would expect that the impedance increases by about a factor of 11, roughly. Incidentally, what are all these low-pass filters here for? Just because we had another.
Reduce noise.
Yeah, exactly. Because I don't. Later we are going to look at the noise from this thing, and then we don't want to get confused by noise from the biasing network. In reality, of course, we very well may get noise, extra noise from the biasing network, but then we want to account for it separately, right? Because there are different ways to deal with that noise as opposed to the noise that is actually in our signal path. All right. So now the SPICE simulation for this is on the next slide, but let's not turn there. Let's try to play SPICE ourselves, because if we manage to do that, we understand a whole lot more than if we just look at the pretty picture. So load the SPICE code and let's play SPICE. Okay, so now you will need to use less zoom to show the entire page. Okay, good. So here's frequency, and here is C out. We'll make this easy. We'll start with just, and these are on log scale, and this is, of course, absolute value, right? Make this easy. Our gain booster, of course, consists of just a simple current source transistor, a cascode on top of that current source transistor, and a gain booster on top of that. So we'll handle one at a time. Okay, we'll start. What's the output impedance of just the current source? Well, that's going to be something like this, right? And then somewhere at a sufficiently high frequency, it's going to fall down. Why? Well, because we have some capacitance at the drain end of our transistor that is going to become very low impedance at sufficiently high frequency. Right? Okay, so now we put, so this is no cascode, just current source. And then this is, of course, RO1, if you want. Now, we set a cascode on top of this. Well, the cascode, like your colleague said, the cascode boosts this thing to basically, by a factor of, this goes up by a GM RO, or an AV0, right? And then, that happens to us up to a certain frequency. Up to what frequency does the cascode boost the output impedance? Yeah, and what is that? You please use the microphone. You will have to fight over it because you both have the answer. You just don't dare to say it. Remember, it's 5% of the grade, so it really pays.
So I guess the first pole of the cascode transistor.
Right, so we actually looked at that. That's the omega t, roughly the omega t of the device, right? So somewhere around the omega t, this is going to tank. And then of course, then ultimately after that, we're just going to be limited by the impedance, the output impedance of the single transistor. We still have that there until that thing loses traction also. Okay, and then finally we get the 1 plus T additional boost on top here, and that's going to roll off also. And here, of course, the bandwidth is going to be whatever bandwidth we have on our gain boost amplifier. Right? So that's the output impedance of the entire thing. Looks pretty gross. Well, sort of like a waterfall. Eh? Okay. Now, in reality, you probably are not going to see this output impedance. Why not? Because in practice, you built this current source to use it somewhere, and this current source probably was tied to the output of an amplifier. Right? So when we at the output of that amplifier, we also have a big capacitor because the amplifier has to drive something, right? That's why we have the amplifier there. So in reality, this whole thing is going to be in parallel with some capacitor that's hanging on this node. Well, what's the impedance of this capacitor? Well, the impedance of that capacitor is going to be something like this, right? So this is 1 over SCL. And to the overall impedance of our circuit, well, that's the parallel combination of what we just had figured out and this capacitor. So altogether, the gain is going to look something like this. Then here, it's this guy that's going to dominate, the capacitor that's going to dominate. Then here, something interesting is going to happen. If we think about the parallel combination of the two impedances, right, it's always the smaller impedance that wins, yes. And in this case, of course, the smaller impedance is the capacitor. Up here it was the resistor, but here it's now the capacitor. But when the resistive part here gets a little bit higher impedance, well, then we're going to get a little bit closer to this 1 over SCL line, right? So here there is a little plateau. It's almost invisible, and if you had plotted this with spice, it would have been completely invisible. So there is going to be a little plateau, and then it starts falling again, because it cannot possibly cross this line, right? It's a parallel combination. It's bound by the lower of the two impedances. So it's going to sort of hug this thing, and then it's going to fall down again. And actually the same thing, and this is no longer on my plot, but you know, it is kind of irrelevant. There is another plateau here, but you know, not going to see this. But this plateau definitely is there. And it's a problem. Why is this plateau a problem? Well, first of all, well, in an amp, when we use this amp, when we later we're going to analyze this, when we use these current sources in amplifiers, then this plateau here, of course, I mean, something that first rolls down, then it's flat, and then it starts rolling down. There got to be a zero, and there got to be a pole. So there is a pole-zero pair present at these two frequencies. They're very close to one another. That's why we don't see them in the SPICE plot, unless, as good designers, we know that they're there. We're going to look for them, and we're going to zoom in there, right? Okay, so there is this pair of poles and zero, and they're usually referred to as doublets. And what they do is they set the settling time constant of our amplifier. So ultimately, this at our amplifier, we may when we use this, we may use a lot of feedback, unity gain feedback, and so on. So the time constant of our amplifier may be something like this, very fast. But the settling time is going to be determined by the doublet if the doublet is at a lower frequency. We're going to analyze this. There is a bit of math that we need to do and sort of understand this completely. It's going to happen, but it's going to take a few weeks. For now, all I'm going to tell you, these doublets, even though they cannot be seen on the SPICE AC plot because it's just too small, they're too close together, they're important. Don't just ignore them, right? Okay. So, okay, now we have to clean up a few things. Well, first of all, we can look at the SPICE simulation. Well, I think you probably can see this better. SPICE shows exactly the same thing as our analysis. It exactly confirms this terracing and so on. Of course, I set up things a little bit in order to get that. Incidentally, there is a paper that describes and analyzes this circuit, and you probably want to look at that. It appeared in the Journal of Solid-State Circuits, which you can get from the online library here at Berkeley, for example. Journal of Solid-State Circuit, that's this red journal, the journal of this field, and it appeared in December 1990, and the authors were Bult and another one. Okay, so with this you can, well, I give you the page too. It was on page 1379. Okay, so there is an article that discusses this. And it also discusses a few other things. It tells you about this doublet story, but it also tells you, heck, I mean, there is a feedback loop. And whenever we have feedback, we got to be very careful. Why? Yeah, exactly. The minute we have feedback, we can have also instability. And so that's easy to overlook, right? This feedback loop here, it's not the overall feedback loop around our amplifier. We haven't even shown the amplifier. We are not quite there yet, right? But there is a feedback loop, and this feedback loop deep inside our amplifier can go unstable, and if it does, the whole amplifier is not going to work. So we need to analyze this. Well, there is the amplifier itself that probably is going to have some pole. I actually set the bandwidth of the amplifier with this circuit here. Now a little more zoom would be just fine. Yeah, thank you. So I gave this a bandwidth of 10 Hertz. So this is actually not for the noise. This low pass filter is just to make an amplifier with a 10 Hertz bandwidth. So actually in this circuit here, this here would be 10 Hertz. This frequency, right? For our example, you can verify that by looking at the SPICE simulation. Okay, so generally this amplifier, because it has a, well, not really high gain, has a gain of 10. But just at ISSEC, I don't know whether you saw that paper. There was a guy, an incident student from Berkeley, who used an amplifier here that really had high gain. In fact, in order to give it very high gain, the guy used gain boosting in the amplifier that implements this thing. Okay? And then ended up with an amplifier with overall gain of 130 dB. At least that's what he said he got. You can't, it's very hard to measure and prove that you got 130, because at that level, we have to be very careful when we do such extreme stuff. Strange things can happen. For example, if you have an amplifier, if you have just a tad bit of feedback, then that tad bit of feedback is going to set an upper bound on the gain you can achieve. Well, 130 dB going to 10 to the whatever is a huge number, right? It's like 2 million or so, more than 2 million. Right? Then just a very small amount of feedback can be a limiting factor. And so very small feedback can be like a thermal feedback, right? So you get the thing heats up a little bit, there's the voltage increase on the other end, and a little bit of that heat couples back into the input. Well, that's a feedback loop. Normally we don't need to worry about, but if you sort of go too far, then stuff like that can happen. So it's just a warning, right? With SPICE, no problem. SPICE happily simulates 10 million if you want, but in reality, you may or may not get that. Okay, so detour ended. So then there is another pole in this feedback loop. That's our cascode, our cascode transistor. And we said that it has basically at omega t, or a fraction thereof, omega t. There is another pole. Well, for our loop to be stable, the bandwidth, the unity gain bandwidth of this loop better be less than the non-dominant pole, right? Otherwise we get peaking or even ringing or oscillation. So the unity gain bandwidth of this thing, this frequency here, better be less than omega t2. Okay? Otherwise we get instability. And well, what is this frequency here? This is omega t2, right? That's why. What limits the cascode? Well, omega t2. So apparently, that's quite interesting. First, when I saw this circuit, I said to myself, well, gee, I want to build a very fast amplifier. And now I want that amplifier to somehow be better. And I need another amplifier to do that. Do I need a yet much faster amplifier? Well, the answer is not only no, because it's anyways the capacitor that determines the gain at higher frequency, not that amplifier. It's only a low frequency where I need this extra gain. At higher frequency, it's the capacitor. So first the answer is no, I don't need a yet faster amplifier. But the other answer, ironically enough, is if I were to use an ultra-fast amplifier, probably would be a bad deal because the thing would be unstable, right? So we actually generally don't want this amplifier to be too fast. But on the other hand, we also don't want it to be too slow. Why not? Because this frequency determines where we've got the doublet, right? And the doublet, in order to get fast settling, has to be at a frequency that's higher than the closed loop bandwidth of the amplifier that we're building out of this thing. And again, I promise that we're going to analyze that more, but it's good to be aware already. And I hate to say wrong things.
Quick question.
Yeah.
That frequency that's just below omega t2, what sets that frequency? Is that the amplifier
unity gain bandwidth of the booster amplifier, right? It's basically the unity gain bandwidth of this feedback loop here, which because this gain is approximately 1, which we determine to be the gain of this thing. So generally, this will be a transconductance amplifier. Again, if you go to that paper that I mentioned, you'll see one possible implementation of this. So that would be a transconductance amplifier. And so the load capacitance, CGS or so, Millard, right, presumably would set the bandwidth. So we don't need too much GM there. Right? If you put too much GM into this guy, the ring's bad. Okay. There is one other thing I wanted to say about this circuit. Just a little bit intuition. Well, we've said before that, well, because we use feedback and we've analyzed this stuff in some undergraduate class, right, the output impedance increases by 1 plus t, by factor of 1 plus t. Okay, so that's fine. A slightly, perhaps a little bit more intuitive explanation is as follows. What does this amplifier here really do? It compares the voltage at the source of the cascode, and more importantly, the voltage at the drain of M1 here. It compares that voltage to the bias that we set up with some appropriate bias network. Then it uses feedback to produce an error signal that it applies to the gate here that counteracts any deviation of this voltage from this one here, right? So really what this circuit here does is it pins the voltage here at the source of the cascode and also necessarily then at the drain of M1 to a very constant value, namely basically what we've set up here with our biasing circuit. Well, if the voltage, the VDS across M1 is constant, doesn't change at all, and the VGS is set anyways, and the size of the transistor presumably doesn't change widely once we've fabricated it, right? And then everything's constant and given on M1. Well, M1 has no alternative, but always run exactly the same current. So well, if it always runs exactly the same current, then it kind of looks like this, right? It's flat here. Well, flat means the output impedance infinite. So that's another way to look at it. In fact, also for the cascode, really, one way to look at the cascode or the boosted cascode is it pins the voltage here at the drain of the current source transistor. And it makes it easy for this current source transistor to always put out the same current. That's another way to look at it. All right, now this looks almost like something for nothing, right? We can, before we had said, well, if we want to further increase the output impedance of a cascoded circuit, we're just going to stick a second and third and fourth and so on cascode on top. And if we do that, then of course that's going to cost voltage headroom. And so there is an obvious price to be paid. Now we have this feedback loop, and that kind of goes on the side. It doesn't cost any additional voltage headroom. We just use a better and better amplifier here, and the output impedance of this thing is going to go through the roof. So what gives? There ought to be a price. So we've seen already the potential gotcha is this business with the doublet. But the other thing is noise. So now I load. So here, incidentally, here I now actually made a real amplifier to. I use a common source amplifier as the gain boosting amplifier. So this gain of 10 or whatever it now happens to be is actually generated now by this amplifier. And the reason I use the real amplifier is I want to get the noise from this amplifier also. And how do I best build a noisy amplifier in SPICE? Well, I build an amplifier, right, as opposed to using an ideal circuit. So that's why I did this. So and then I loaded my in order to look at noise at the output, I really need to have a reasonable load here. So I just said, well, instead of feedback loop, that would have been a little bit too much for setting up just an example here. I put the load resistance of just a k ohm here, and then also low capacitance. And then I ran noise analysis on this. And again, I make my 3 different setups so that I can compare what's going on, right? And we've already looked at that before and said that the cascode at low frequency really doesn't contribute much noise at all. So here is the noise density as a function of frequency. So that's just the density in volts per root hertz. And again, at low frequency, there's really no difference. However, at high frequency, the gain booster gives us a little blimp here. Big deal. I mean, who suggests that we should worry about this? you know, this little difference here, this extra noise. Who thinks it's an issue? Who has no opinion? Therefore, you all think it's no issue. Yeah? Good luck as circuit designers. Okay, so in order to figure out whether it's an issue or not, I integrate it now. So this is the total noise, right? The noise that we're going to see in our A to D converter. And of course, if I integrate only up to here, I get very little noise, and then it goes and saturates here. And so this is just a cascade. This is with the addition of the gain booster, right? That now includes this little hump. It's a big deal. And why is it here a big deal? Right? This is log. No, this is actually linear scale. But yeah, I get 20, 30% extra noise, right? Extra noise. So why? Why does it look like a big deal here when it doesn't look like any deal at all up here? Yeah, it's the old hat, right? This is log scale, and so this here is hundreds of. This is actually this width here is about a gigahertz, and down here, well, this is about a kilohertz. So obviously, I mean, this noise doesn't count, right? Also, the flicker noise that we get here. This is. It looks bigger than this area, but it's totally negligible. Forget it. Doesn't matter. Because that's over 1 kilohertz. This is over a gigahertz, this little blend. So got to be careful about that. So we can get extra noise from our gain boosters. And of course, the gain boosters also can do dissipate extra power, typically in a similar penalty, 20% or so extra power in the gain boosters. Well, it adds up, right? So I'm not advocating against using them at all, but I say that you got to be careful, and it's not completely a free lunch. Sometimes when we actually build an amplifier, there is more stuff, right? We actually have this amplifier that includes a gain booster, and then we have a switch, and then we have a capacitor, and we really care about the total noise sampled onto this capacitor. Well, then we have the output impedance of this guy and the noise from this guy, and then in series with the switch, with the on resistance of the switch, right? That depending on how that resistor is scaled and so on, the thing actually may start rolling off further earlier, and then we might attenuate this noise hump with our switch on resistance. So here in 240, for simplicity, most of the time when we're going to simulate, even in the project, when you're going to simulate our amplifiers and design them and so on, we simply neglect this switch. Right? We just don't put it in. We just say, well, the switch is closed, and then we want to know how our amplifier settle and how much noise it dumps. But it's not quite accurate, and sometimes, of course, it's bad news because the amplifier doesn't settle because the switch has too much on resistance. But sometimes it's good news because this on resistance of the switch filters away some of the noise. So what's the point? Well, ultimately, when you're going to build such a circuit, you're going to fab it. Well, use the design practices of 240, but then spend all the time and ultimately simulate with everything in the circuit because it can make a difference. But here we want, in our homeworks and so on, and in our class, of course, we don't want to spend hours and hours on details, right? Even when they're important. Okay? So here is sort of a zoom in, right? We can see that even the cascode, the current source, that's the blue line, it clearly dominates the noise at lower frequencies. But then the cascode, this purple line here, it comes way up at higher frequency. And so even the cascode, without the gain booster, potentially could give us a little noise penalty. Or maybe not so little, depending on how things are. And And then if you have the gain booster, well, then we have yet extra noise. And you know, I sort of cooked this example, you know, of course, in order to show that the gain booster does contribute noise. And some of the choices I've made, if you go back to my SPICE text and so on, you will see some of the choices are somewhat unrealistic. I added a lot of capacitance at the source of the gain booster, so which really probably wouldn't be there. But on the other hand, most of the time when you build a gain booster, you also have more devices, not just this simple common source stage that I used. And so you got to be careful, right? It really can add noise. Okay, so well, that's the deal about current sources, right? If we want low noise, we throw a lot of voltage at the problem. If we want high output impedance, then active solutions, transistors, are going to help. First, using a longer channel transistor is going to help. And in particular, my observation is that most of the time when you use just the minimum channel length, then you really get low output impedance. If you just go a tad higher, you know, increase from 0.25 to 0.35 or something like that, or even 0.3, that you win a lot. But beyond that, we really can't get that much extra gain or output impedance from channel lengths. So then we're going to use cascodes, and if that's not enough, then we're going to use gain boosting. And if that's not enough or not applicable or whatnot, or we are afraid of or have problems with the doublets, then we're going to use multi-stage amplifiers. Hey, there is one more thing that we need to look at when we build current sources. I mentioned already a current source, so its job is also to replicate the current accurately. Now, in a biasing network, a couple of % of error may be tolerable. But sometimes these current sources also are used for D2A converters. Actually, very often, that's the main way on how to build D2A converters. In fact, how do we build a D2A converter? It's basically, there are other ways also, but this is a very common one. We will build a whole bunch of current sources. We ratio them, and this is 1x, 2x, 4x, 8x, and there probably are going to be more. And each of them has a switch in series. And the switches are controlled by the digital input to our DAC. And then they produce a current here, I out, that is just proportional to the digital input. So in this case, of course, we want that these current sources really produce exactly the right amount of current, right? And a few % mismatch. Oh no, I mean, that's not going to cut it. So in that, so for that we have to talk about matching. So when we talk about matching, we can distinguish, and I think we already talked about that a little bit, between systematic mismatch. Right? If, for example, we put resistors in the source, well, we're going to get every single current source is going to be off because of the resistance that's there. Likewise, if VDS is not the same for both transistors, well, then we get a systematic mismatch. That's why we had this transistor M5, right? Definitely want this here. But then another thing is that, well, if the mobility or COX or stuff like that is different, or the threshold voltage is different, then that can also lead to systematic mismatch. When we build circuits on a wafer, then typically just because of, for example, processing gases getting to our chip, so we're going to get so-called gradients. And in fact, if you are friendly enough with the fab, they're going to give you data that looks maps like this. They measure the threshold voltage across your wafer, and then on sort of lines like this, here the threshold voltage for all devices may be 500 millivolts, here maybe 550, and here it may be, let's say, 600 or so, right? And so fortunately, our chips are not as big as the wafer, right? And so this effect may not be as bad as it looks here. But nevertheless, if we have a current mirror that is sort of arranged here, one transistor and the other transistor is here, then clearly this transistor is going to have maybe a millivolt or two lower threshold voltage systematically than the one over here. And I think we already mentioned that. Well, maybe common centroid or so layout ideas or so may overcome this problem. So let's suppose let's suppose that we've done everything right, M5 and so on are there. There is no source resistance to speak of, and we have a common centroid layout. So the systematic mismatch really is gone. But then we end up with random mismatch. And kind of the key contributors in this random mismatch are W over L ratio mismatches and threshold voltage mismatches. And of course, let's lump into this also mu C oxide. But also mismatch. So let's assume that we had a current mirror something like this that had where we had mismatches, W over L mismatches between these two transistors, nominally identical in practice just because of random variations, not systematically, a little bit different, and also threshold voltage mismatches. Okay. Now, when we analyze one of these things, something like this, then again, these are large signal parameters. So we need a model. Fundamentally, we just need a model that exhibits these large signal parameters. So for that, again, we go back to the square law model. Not that big a problem here because we are looking at errors. Errors are small. So making an error on an error generally produces a second order error, right? 1% of 1% is 0 for an engineer. Right? So we usually get away with this approximation. Okay. So the other thing about this is that, of course, the square law model, or in general large signal models, they're nonlinear, and it's a little bit takes a little bit setting up the problem just right to analyze these things. So there's here a little bit insight into how to arrange the equations out. So anyways, I've set up here the two transistors that have different threshold voltages and different W over L's. And then I define delta ID, and I also define the nominal ID that is just the mean. Right? I do the same thing for the width. And then I solve this equation to calculate the relative error. And this relative error, if you can use more zoom just on this equation, please. So the percent mismatch, current mismatch, is going to be just equal to the percent mismatch in W over L, and then this other term here. And this other term here deserves a little bit more attention. It includes it measures the mismatch in threshold voltage, but it also includes this VGS minus VTH, which roughly is V star, right? What does it say? Well, what this term says is that in order to get small mismatch here, I of course want to make this term small here. I want to use a large V star. Right? And that, with hindsight, also is kind of makes sense. Why does it make sense? Why is it reasonable to use a large V star in order to reduce mismatch arising from delta VT? Yeah, you just need to use the microphone and then say it.
Because small voltage variation around if you have a large overdrive, a small voltage variation doesn't change your current very much.
Precisely. I mean, the sort of the keyword that I like to use is GM. GM gets small, right? And GM really is amplifying delta VTH to produce a delta ID that we don't want here. Here again, as we said earlier, we want a small GM. Sometimes small GM is a good thing, right? And unfortunately, the only way to get that small GM is using a large V star. So here, invariably, immediately we see a conflict, right? Of course, we want a small V min. That translates into a small V star. But we also want to have low noise. That translates into a large V star. And we want to have good matching, and that also translates into a large V-star. So voltage is pretty precious, and we're going to fight over it, right, in our design. In the homework, there are a couple of problems that I posted a new one today. There are a couple of problems that I think you will find very rewarding if you don't just grind through and throw it into a drawer when you're done. One of them is looking at building an amplifier, simple common source amplifier, nothing complicated at all, that is now loaded with a real current source. And it specifically asks you what the result means. Look at that, and you will find you will get profound insight on how to choose V-star in such an amplifier. Okay? When noise is an issue. The other homework problem asks you to compare MOS transistors and bipolar transistors in terms of noise. Again, there are cases where you absolutely want the MOS, and there are cases where you absolutely want the BJT. You want to know when which. Maybe you have by CMOS technology, right? You want to use the right transistors to start. So the homework isn't busy work. If you look at the result, it's actually profound. You will remember the result. Okay.